Okay. Good morning, everybody. My name is Albert Castellanos, and I am an Erasmus student of Industrial Engineering coming from University of Girona. Today, I'm excited to present you with my semester's project on the inverse kinematics of a Stewart-Gough platform. And this project is closely linked to Pau's project from the previous presentation, with that I work on the software part and the underlying mathematics. Now, here's an outline of today's presentation. Firstly, I'm going to give you some background of what Stewart platforms are. Then I'll discuss the project's main goal. And before going into the main section of the presentation, which is the software, I'll introduce you to inverse kinematics. Now, after all of that, I'll talk about how we implement it into a real-life prototype. And finally, I'll make a summary and I'll give some ideas for a future follow-up project. So what exactly is a Stewart platform? Well, a Stewart-Gough platform is a type of parallel robot that can move along the three axes, X, Y, and Z, and can also rotate about these three axes. That means that it provides it with 6 degrees of freedom. Now, there are several types of Stewart platforms, but the original one is the one you can see right here in the video, which is composed by 6 linear actuators that provides it with the movements of rotation and translation. Now, the applications of the Stewart platform are usually when you require precise movement and control, such as robotic arms, surgical robots, and flight simulators. Now, the foundation of my project is the Stewart Platform Simulator by Robert Eisele, which is a software. And the main difference with the original Stewart platform is that this one is supposed to work with cheap rotary servos, meaning that taking the real platform into a real-life prototype is much more affordable and feasible. Now, in basic terms, I'll get deeper into it later, but what the software allows the user is to simulate a Stewart platform with the specified physical parameters. Now, given this background, let's dive into the main project goal, which is to attach a laser pointer to a real Stewart platform and make it project shapes into the wall. Now, before talking about how we achieve this goal, allow me to make an introduction on inverse kinematics and show how it's relevant to my project. By definition, inverse kinematics is the process of determining the joint parameters needed to achieve a determined position and orientation of the end effector. That means that in our Stewart platform, what is necessary is calculating the servo angles of the rotary servos in order to achieve the platform's orientation and the platform position that we want to. Now, luckily for me, the inverse kinematics were already solved by the developer of the original Stewart platform simulation and implemented, which is Robert Eisele, and he explained it very well in a paper that he published on this topic. And he used Quaternion rotation these calculations. So Quaternion may sound unfamiliar to some of you, so let me make a brief introduction about it. Quaternions are an extension of complex numbers, and without getting into much detail, we could think of them as a 4-dimensional vector that has its own properties when it comes to operating with them. Now, just like an imaginary number, it's composed of the scalar part, or the real part, and the vector part, or the imaginary part. Now, in our context of the Stewart platform, we use quaternions to calculate rotations in the 3D space. That allows us to avoid some of the pitfalls that other methods have, like Euler angles, such as the gimbal log. Now, it's also really smooth and continuous, which provides a real precise control for the platform and is essential for our project. Now, with the quaternions explained, this is all the theory that will be in the presentation. And now that the mathematical foundation is clear, allow me to get into the main section, which is the software part. So the original software is written in HTML, CSS, and JavaScript. And what it does is it recreates the platform with the specified parameters, but it can also run predefined animations. And as you can see here in the video, it can follow SVG paths in the horizontal plane. Now, SVG images are composed of lines and shapes instead of pixels. And that means that we can resize them without losing any quality. So what the software allows users to do is to input their own SVGs and draw them like you can see here in the horizontal plane. Now, another really important function of the program is that we can calculate the servo angles of the platform in any specified instance. That will be really useful later on. Now, to explain how this software works in the inside, I've made this scheme on the pseudocode. And how it works is when the program first executes, it initializes the platform with the specified platform parameters. And then once that is done, it reads the SVG that we want to run. Now, from there, it creates an animation array containing all the steps of the animation and the data for the animation to run properly. Now, inside this box, everything you see here is going to execute for all the steps of the animation. So firstly, what it's going to do is get the position of the platform required for that precise step. And once we got the position, it applies the inverse kinematics calculations to calculate all the other positions of the elements of the platform. Now with that, we can redraw the platform to the new position, and then this loop goes over and over again, so that it will finish until when the animation is over and getting the desired result that we want. Knowing how the original software works, I think it's time to get into the main modification that I made into the software, which is the projection of the SVG onto the wall. Now, here on the left side, you can see the original, like the starting point that we had, that was the SVG on the horizontal plane. And then in the second step, we can see that I was able to translate the planes from the horizontal plane to the vertical plane. That can seem like a really simple step, but in my case it wasn't, because it took me more than 1 month to achieve, since I had to previously, before making any modifications, understand the code thoroughly, and I had to study all the JavaScript syntax because I had little to no background on it before. So you can see that the second step, there's a problem with it, and the problem is that it's only doing translation movements, and that's the difference between the second step and the final step, which is also relating on rotation movements. That means that we're no longer dependent on the servo range to make the projection, and we can increase the size almost as much as we want to. Now, to explain this transformation, there are 3 variables that are essential to the platform's movements, which are, in the first hand, the drawing size, which is pretty self-explanatory and is the size of the canvas where the SVG is going to project to. And on the other hand, we have these 2 variables that are measured when the platform is in its resting position, meaning that the laser pointer is pointing straight into the center of the wall. Now we have firstly the distance to the wall from the platform's origin, and then we have the rotation axis offset, which is the distance from the platform's origin to the center of rotation. That means that if we take this rotation axis offset and put it in the center of the platform, then when it moves and projects the SVGs onto the wall, it will only rely in rotation movements. However, when we take it further away, the farther away we take it, the more translation it will make. So the key here is to find the sweet spot depending on every user's needs, so it can be modified. Now here, to solve this problem that I had, the basic thing that we had to do was, knowing the drawing's coordinates that we already had in the previous step, find a way to move the platform and rotate it for the laser pointer to point exactly to those coordinates. So that was solved using basic trigonometric functions, and you can see them in the code's documentation in case you want to check them out. But yeah, this is how it was done. Now, to implement all of this into the code, I'll show you first the pseudocode that I discussed before, which is how the code worked. And what I did was only adding an intermediate step that converted the 2D drawing coordinates into the 3D platform coordinates and rotation. And then the rest of the code, of the execution, is exactly the same as before, but with this intermediate step that would perform the calculations of the projection. Now, in case you're curious, here's the function that I implemented. It's not really that long, it's only 29 lines. But I would say that the hard part about it was knowing where to put it in the code and how to implement it so that it would work with the rest of the software. Well, apart from the main modification that I did, which was the projection onto the wall, I also created a user-friendly interface. I added the possibility to convert text that you input into the browser into SVG and make an animation out of it. And finally, I added a menu where you could change the parameters of the drawing in real time and see how it affects the behavior of the platform. Now, the final and most important implementation I did was adding a button that could generate a text file with containing all the sequence of the servo angles of one concrete animation. That way, the content of that text file could be used into a C++ header and recompiled to use it into the Arduino board to recreate the platform's movements into the real life. Now, all of these implementations, we're going to see them in the demo afterwards. That brings me to the last part of the project, which is the real-life implementation of the platform. Now, for the design part, Pau took care of it, my colleague, and he explained it very well in his presentation. So I'm going to skip to the electronics, which were made possible by my tutor Jürgen. And what we used to run the platform was the COSMOS OpenC3 software with an Arduino board operating on C++ and using the TiSCo software library, also developed by Jürgen. Now, with everything set up, we ran some tests, and obviously the results weren't really good in the first instance. But after a few tries and a lot of debugging, we managed to achieve these results, which look, in my opinion, much better, and even the letters are well readable now. Nonetheless, we still had some issues that remained unsolved to this date. And the main issue we had is a little bit of warping in the top side of the projection. And that may be due to maybe an imprecise servo calibration or the measurements of the physical parameters, or even maybe the servo quality, which, as I said, we were working with cheap servos, and the precision maybe is not that accurate as we want it to be. And these possibilities, I made some tests to prove them, but I didn't really reach any precise conclusions. So we're not sure if these are the real cause to the issue. Now, to finish, I will make a brief summary of the project, focusing mainly on the principal objective. And I would say that it's safe to say that we achieved it by thoroughly understanding and documenting the original code, then successfully modifying the code to make the projection onto the wall, and finally implementing it into the real-life prototype of the platform and having the desired result. Although there are still some issues that remain unsolved, I think that we accomplished the objective. And finally, I'll give some ideas for a future project. And the first thing I would do would be to translate the JavaScript software with the inverse kinematics and the Quaternion calculations into the C++ software that controls the Arduino board. And that way, we wouldn't have to generate the text file into the JavaScript software, then recompile it into the C++ code, and then run it onto the Arduino board, which would save us a lot of time and as well a lot of trouble. Now, the second thing I would do would be to, apart from solving all the issues that we had before, to find a way to recreate the real-life platform into the screen and control it live from there. So, for example, using the mouse to control the platform or input the position from the keyboard and see it happen in real life. That would be, there's also endless possibilities to this project, so I think that would be a really interesting project. Well, with that, I conclude my presentation. I really hope that you enjoyed, and if you have any questions, I'll be happy to answer them. Now we can proceed to the demo. No.
Right, I'll start with that.
Yeah.
So same software. While we are waiting, you should explain why it's always not a perfect straight line.
Yeah, since the servo motors we have a sequence of steps in the text file that we compile in the C++, and we have the positions of the steps, but in between those steps, we really don't know what's happening inside the servo motors. So we know that from one step to the other step, it's going to be the position that we want, but since this is not linear, then between the steps, we have no way of knowing where the platform will go. So that's why it's a bit jittery. And that's because in between the steps, we really don't control the servo motors. Yeah.
Thank you very much.
And yeah, now I will make a demo of the software. Yeah, so here's the software, where you can see that in the top side, there's all the SVGs that are loaded. In the right side, top part, there's the current servo angles that the platform is at. And then here you can see the representation of the platform. And here are the functionalities that I explained before, such as the text to SVG, the parameters that we can modify on the fly, and also the downloading of the servo angles. We can also change the view of the camera just for visual purposes, and we can run the SVGs by clicking at them. For example, this one, and we can switch between the final view and the live drawing. So just like the real platform. But of course here we don't have the issues we have in the real life platform. Now we can also change the distance, the rotation axis offset. For example, if I put it to 0, now it will rotate. It will only rotate. It's not translating. And we can change, well, the distance to the wall. And we can also write text here and convert it to an SVG. For example, I would write hello world. And you can see that it writes it. And we could download this animation into the text file and then bring it into the real life. So that's basically the functionality of the code. Yeah. Now we can proceed to the questions.
So what is definitely not solvable is the fact that, especially vertical lines, that they are not straight. Because we have no control of how fast or in what order and what speed the servos move from one point to another. It's point control and not motion control, actually. So if you want to improve that, then we have to forget about the cheap servo setup and go to much more basic controllers like stepper motors, but then the electronics get much more complicated, and that's not the goal of our education. We want to focus on the mechanical, and the mechanical is what it is. We want to spend our time on that.
The initialization of the platform, how does it work?
Yeah, so basically there's a function that calculates all the position of all the elements of the platform depending on its physical parameters. So I will show you the platform to explain better. Yeah. So you enter all the parameters of the platform before in the code. So you enter the rod length, the horn length, now the radii that compose the platform and the base, and from there the software makes the calculations to know how the platform should look. So that's when we say that the platform is initializing.
Has the software to calculate every point?
For calculating every point.
Maybe it's the processor is not fast enough, then the calculation to have the straight lines.
Well, it's more an issue of, because it's not actually lines that it's calculating points. So if we have the O of the Odyssey logo, it's instead of lines, it's calculate 1 point. Well, a lot of points.
The software had to calculate every point.
Yeah, but it has no problem doing it. It's really fast and the way it works. And really the issue here is the real life platform that has these limitations. But in the software side, I think there's no issue with it. It can really do a lot of calculations in really fast.
Like now we are showing the pulses, so you can explain the actual amount of pulses that are in the code.
Yeah, so now there are little points drawing, and every little point means one step of the animation. Between every point, we don't know where the servos go. That's why the jitteriness. So this animation has, if I remember correctly, 1,600 steps, something like that. Every step is one little point you see here. We also, to make sure it was correctly working, we made an animation that consisted of 3 squares, one inside the other, of really few steps. Like we had like 50 steps So we could slow down the animation to a point where every second it would make one step, and we would see that it would complete the shapes. So that's how we managed to see that it was actually properly working. Thank you for listening.